Well, this week we're also working in lesson 3.5 with higher order derivatives. As you know, derivatives are functions, and these functions also often have derivatives themselves. We call these derivatives of derivatives, higher order derivatives. First, let me show you the notation that we use for higher order derivatives. If we are given a function y equals f of x, then, as you know, the derivative of y can be written in this notation, f prime of x. And in Leibniz notation, that would be dy over dx. We see them both ways in our text and in the problems that we do. For the second derivative, what we'd be doing is taking the derivative of f prime of x. But we don't usually write it with this notation. Instead, to make it a little simpler, we write f double prime of x. That means the second derivative. In Leibniz notation, we use little superscript 2's. So it's a d squared, dx squared. That means the second derivative. And y would be right here. And the third derivative goes the same way. We'd be taking the derivative of f, then taking the derivative of that, and then taking the derivative of that. And to clean that up, we use just a triple prime, meaning the third derivative. And in Leibniz notation, you can probably guess that we're going to use a little superscript 3 or cube to represent that we've taken the third derivative. So just get used to this notation. You really should be able to do either the prime notation or the Leibniz notation in each case. So let's get down to business and work on some derivatives. In example 1 here, I'm going to find all of the derivatives. Find the derivatives of all orders of f of x. I'll start with the first derivative, f prime of x. We're going to use the power rule, and we get 5x to the fourth minus 12x cubed plus 12x squared. That's a 12. Minus 4x plus 1. The derivative of a is 0. The second derivative, meaning we take the derivative of f prime, we go through the whole process again. This would be 20x cubed minus 36x squared plus 24x minus 4. Derivative of 1 is 0. The third derivative, (60x squared minus 72x plus 24. The fourth derivative, which you'll typically see written as a little 4 in parentheses. I guess I should have told you that on the notation screen, huh? Once you get past 3, we'll start using the regular numerals in parentheses to indicate the derivative that we're on. So our fourth derivative is 120x minus 72. Our fifth derivative is 120. And then every derivative after that. So for n greater than 6, greater than or equal to 6, the nth derivative is going to be 0. So the sixth derivative is 0, the second derivative is 0, and so on. So we've covered all the derivatives of all orders of this function f of x. And the best way to get some experience with these higher order derivatives is just to do a bunch of examples, and that's kind of what you'll be doing in your practice exercises. Here we're asked to find the third derivative, so I'm going to do the derivative 3 times. The first derivative, y prime, will be 2/3 x to the negative 1/3. Be careful when you're subtracting 1 from 2/3, you get negative 1/3. The second derivative is going to be negative 2/9 x to the negative 4/3. Negative 1/3 minus 1 is negative 4/3. And then the third derivative is going to be positive 8/27, because 4/3 times 2/9 is 8/27, x to the negative 7/3. In radical form, that would look like this: 8/27 times the cube root of x to the 7th. Depending on what your situation is, you may decide to use either one of these forms. Now, one thing you should keep in mind is once we find this first derivative, we are now talking about negative exponents. Let me just show you why this is a big deal. The domain of the original function, y equals x to the 2/3, is all real numbers. But the derivative and the subsequent derivatives all have an undefined point at x equals 0. If you write this in radical form, the first derivative, this is going to be 3 and then times the cube root of x. And you'll see here x cannot equal 0. And that's true for these other ones as well. So we need to be aware of that. The domain of these functions does, the domain is affected by the derivatives. Of course, these derivative problems get more complicated. Our good friends, the product rule and the chain rule, often rear their ugly heads. In this case, this looks like a fairly harmless composition, but when we're asked to find the second derivative, things get a little interesting. Let's do the first derivative first. We just follow the chain rule. Y prime would be 3/2 times 2x squared plus 3 to the 1/2 times the derivative of the thing in the parentheses, the u, which is 4x. And if I clean that up a little bit, I get 3/2 times 4x is 6x times the square root of 2x squared plus 3. That's the first derivative. To get the second derivative, we have to recognize that we have a product here. We have 6x, which we'll call our u, and we have the square root of 2x squared plus 3, which we'll call our v. Okay? So as I'm setting this up, I'm going to have a u prime. Let me start with u. Let's just write it out explicitly so everybody knows what I'm assigning here. And I'll move it over a little bit. U is 6x. That means u prime is 6. V is 2x squared plus 3 to the 1/2. That means v prime has to follow the chain rule. That's 1/2 times 2x squared plus 3 to the negative 1/2. I need to pause and slide this over a little bit. Times the derivative of 2x squared plus 3, which is 4x. And I'm going to put that right here, now that I've made a little room for myself. Okay, we simplify that, and that becomes 2x times 2x squared plus 3 to the negative 1/2. So now to put together y double prime, we just write out the product rule. It's going to be u times the derivative of v, meaning that would be 12x squared times 2x squared plus 3 to the negative 1/2 plus v times u prime, which would be 6 times 2x plus 3 to the positive 1/2 power. And that's certainly a good start, but as it turns out, we can simplify this a little bit. And that's what we're going to do on the next screen. So while some of you might think this is a perfectly acceptable second derivative, we really need to simplify this expression to get an idea of what this function is really all about. And the first thing we do when we're doing that is we'll go ahead and write it in radical form. this first term would be 12x squared over the square root of 2x squared plus 3. And the second term is going to be 6 times the square root of 2x squared plus 3. And to simplify this a little further, what we need to do is get a common denominator so we can add these two terms. To get a common denominator, we'll have to multiply this guy by 2x squared plus 3. And yes, I understand this is just a huge exercise in algebra with a whole lot of terms and radicals and things, but it's important for us to get an idea of what the function's really about. When I multiply those terms here, here's what ends up happening. This first term is still 12x squared over the square root of 2x squared plus 3. But the second term becomes 6 times 2x squared plus 3. When we multiply those radicals, they go away because they're both square roots of the same expression. And then we end up with a radical on the bottom. This gives us our common denominator. And we can add these two terms together. I'll distribute the 6 here. And I'll get 12x squared plus 12x squared, which is 24x squared, plus 18, and 12x squared plus 18 over the square root of 2x squared plus 3. And so that's the second derivative. And because this term down here in the radical is squared, and then we're adding 3, we don't have any domain issues. We won't have 0 in the denominator. If you'd rather write this in a factored form, you could also put it as, you could factor 6 out of the top and make it 6 times 4x squared plus 3 over the square root of 2x squared plus 3, but I'll let you decide which one you like better. One of the classic applications for higher order derivatives is in physics. So of course remember that our derivatives are rates of change, and the second derivative is also a rate of change, and which is the rate of change of the first derivative, and the third derivative is the rate of change of the second derivative. And so in physics we apply this concept where we think of acceleration as the rate of change of velocity, velocity is the rate of change of position. And so what I've indicated here are the ways that we usually, the notation that we usually use to indicate position, velocity, and acceleration. You're probably thinking to yourself, why is position represented by the letter S? And I wish I had a good answer for you, but I think the real answer is just that P was already taken. But we use S for position, V for velocity, and A for acceleration. And when you're given a position function and you take the derivative, that new function represents the velocity. And then if you take the derivative of the velocity, that new function, that second derivative of position, represents the acceleration. So let's go ahead and see this in action. So in example 4, we're given a position function. Position's measured in feet. This is the position of the body after t seconds from rest. And it's s of t equals 4t squared. We are simply asked to find the acceleration at any time t, meaning we have to find the second derivative. So first we get the velocity, which is the first derivative, which would be 8t. And this is in feet per second. And then we go ahead and get the second derivative, sorry, I said it right the first time, which is acceleration, and that would simply be 8. And acceleration is measured in feet per second squared. Feet per second per second. So you use the second derivative to find the acceleration function. In this case, our acceleration is constant at 8 feet per second squared. Finally, let's tackle an example literally ripped straight from your textbook. A ball is thrown straight up into the air from the roof of a building. The height of the ball as measured from the ground is given by s equals negative 16t squared plus 24t plus 120, where s is measured in feet and t is in seconds, just like the last example. Find the velocity and the acceleration of the ball at 3 seconds. 3 seconds after it's thrown into the air. So what we're going to do is we're going to find these functions and then plug in 3. So that shouldn't be too difficult. Let's do the velocity first. V of t, which is the derivative, would simply be negative 32t plus 24. And the acceleration is the derivative of that, which would be negative 32. Now remember, this is in feet per second, and this is in feet per second squared. So for the velocity, if I plug in 3, I'm going to do v of 3. I get negative 32 times 3 plus 24. Oops, that's a 4. And if I'm not mistaken, that works out to be negative 72 feet per second. Of course, you're welcome to check my calculations there. And then a of t, when you plug in 3, you still get 32. So our acceleration at time 3, t equals 3 seconds, or 3 seconds after the ball is thrown, is still negative 32 feet per second squared. That'll do it for this video. Good luck.